Yeah, hello, hello, am I audible? Okay, so yeah, so this is your last session for your NPTEL course. Like this will be your last problem solving session that we used to meet for. In like every Friday evenings, like which we used to conduct a problem solving session. Where we have did that for 8 continuous weeks, and now like that has been finished. So we have ended with one last session uh, to like uh, summarize the things. And uh, yeah, so this will be your concluding session. So like we'll see like what has gone through but in this entire 8 weeks. Um, like uh, these are the topics basically you went through. So beginning from linear vector spaces, then Fourier series and Fourier transforms, ordinary differential equations, Laplace transforms, delta functions, Green's functions, series solution methods, and so on. So these were broadly the topics uh, that has been focused a lot on this course. So for mathematical methods one, this is pretty much a very decent course structure. For a 8 week course. Uh, yeah. So then we'll see like uh, I mean there are certain things that you may probably come across like for your examination, because last time around uh, there was one person who wanted to know like what would be the uh, questions for your exams that is coming on in a few week time or a few days. So that would be basically like what I can say, like that I mean your that if you have gone through the assignments properly, if you have followed the lectures, if you understood the concepts, then it is going to be a straightforward job for you to attend the questions that would be asked in the examination. So it's not going to be like big problem for you, like if you haven't followed the assignments and other topics that has been taught. So yeah, so it's going to be pretty much straightforward. There is uh, no there won't be a big issue if you have followed things quite well. So So linear vector spaces, like the first topic that was introduced, I think that ran for almost 2 or 3 weeks, and so so this was the like I would say the primary focus on this mathematical methods one course, and it includes a lot of important subtopics. So we start linear vector spaces by understanding what are linear vector spaces, what are vector spaces uh, exactly. So vector spaces uh, you have gone through over and over again. So one more time, like this is what vector space means. Like you like on a certain field F, you basically define uh, certain properties of vectors, and which can be broadly uh, like uh, um, categorized into the uh, uh, properties under addition uh, and properties under scalar multiplication. The properties under addition, they basically satisfy uh, closure property. Like if you have a vector v1 and a vector v2, and that uh, and that addition gives you in some vector which like if the addition gives you some vector, let's say v3, then that v3 has to mm, belong to the vector space v. So the same, I mean, then again in the addition rule, there is another condition that if you are adding two vectors, they in a way that v1 you are adding with v2, and they must be commutative. It, it won't matter in which order you are adding them. So that is v1 plus v2 goes to v2 plus v1. So that is basically a commutative property. So then associativity, like this is again uh, orders matters very least, and then that is the property of associativity. So like uh, yeah, and then you have identity element. So identity element, uh, like there has to be for any vector spaces. You need to have an identity element such that like when you operate that identity element with any element of your vector space, it should uh, reproduce it back. So like identity element itself is is one of the element of your vector space, and but the key feature of it is like when you operate element like v on your identity element, it gives you v. So under addition, so you have to, when you add this identity element with your vector v of your vector space, so uh, this v and e belongs to your vector space v. So yeah, um, and so for and there are other following conditions which goes under your multiplication rules. That is, when you multiply a scalar alpha uh, uh, um, with your element, one of your element of your vector space, then that uh, uh, total value of that basically give you some other scaled vector that is again, yeah, part of your vector space V. So basically, like you define your vector space on a field. So it has to be like something. Uh, yeah, whenever you define vector space, it has to be defined on a field. Like for example, when we are talking about like um, for example, like in your Cartesian system. So we define uh, like for example, or let's say like a complex number system. So in complex number system, like we say like z is your vector, or let's say z g1 g2 and so on are your uh, vectors on a vector space. Let's say this vector space is uh, C. So if this the vectors g1, g2, g3, and so on are your vectors on your vector space C, that is a complex number. I mean, that is your complex number vector space. So you basically say that like uh, these numbers are defined uh, using complex numbers. Basically, a complex number field exists. So this G1, like this G1 is basically you have x1 plus I y1. So when x1 and y1 are basically real. So like you define this your vector space on a field. So it could be real numbers, it could be complex numbers. So uh, so that defines uh, your field of your field that upon which you are establishing your vector space. So yeah, so then similarly you have other properties in multiplication. So again, when you operate your identity element, that is when you multiply your identity element with one of your uh, vectors of one of your elements of the vector space, then it again that thing has to be uh, reproduce it. Like that is the feature of identity element. And also one thing to remember here whenever we talk about identity element, there must also exist inverse elements. So that was about what vector space is in a nutshell. These properties, wherever you want to define or want to understand any vector space, these properties has to hold. If any of the single property is violating anywhere, then you can just simply uh, let's say that it won't fulfill your conditions of vector space and it won't form a vector space structure. And another interesting thing in your vector space, uh, in your vector spaces are like these vectors, they actually uh, yeah, they actually saw another key feature, that is the inner products. So inner products technically, like if you would see like how much of like in terms of integrals, as we have seen during our past sessions, that like this can be expressed in terms of overlap integrals. Like you basically see how much of your like two bases how much of your two different functions like they say common features or how much of your like in the language of vector spaces, like we have seen like how like what is basically uh, the the overlap region of your two bases, or like how much you can project one of your element on the other element of your vector spaces. So that was technically like the inner products used to do that. So inner products like there are and the uh, important properties of your inner products are like they are symmetric, and which you can prove this way, and linearity, associativity, and positive definiteness. So positive definiteness is again another very important feature of this vector spaces, that again you will see directly in your like, quantum mechanics, like one of the very uh, interesting direct applications that you see normally, that this positive definiteness like is a very key property there. So then we basically talked about what bases are, and uh, yeah. So in basis, like I we used to discuss like every vector spaces by using the ideas like of basis, which means like uh, depending upon the basis of your vector space, that basically defined your dimensions of your vector space, and from that dimensions you can uh, set up a vector space, or basically you could able to construct a vector space using this basis. So and the important feature of this basis uh, uh, for the they should be linearly independent, depend only if alpha 1, E1, and so on up to alpha and En. If there are n number of basis vectors equals to 0, then each of these coefficients of this equations of this. I mean, um, corresponding to each uh, basis vectors, the coefficients has to go in zero, has to be zero individually. Then that defines your basis, and that can if that is so, if this alphas, alpha 1 and alpha 2, each individual going to zero gives you uh, the direct implication that they are linearly independent. This E1, E2, E3, En are linearly independent. So, so this linear independence also results for this following condition, that is that they are also or they also obey this orthonormality condition. So again, like you can try to visualize this if you consider the Cartesian space, like you like how we define unit vectors. Uh, so the same way you can think of, like for an n-dimensional vector space like Rn, you can have n1 number of unit vectors in the same uh, logic you can think of, and that is what again, like they are orthonormal, and using this n basis vectors you can set up any vectors within the Rn vector space. So, and you would see that like they would follow these properties very nicely, which we just saw, like the key properties of a vector space. And further, like there was a couple of theorems that Cauchy-Schwarz inequality, like that basically like is given by this. Yeah, Cauchy-Schwarz inequality again, like we saw like one of the uh, like in Euclidean geometry, this is one of the most prominent feature that you could get in a Euclidean geometry. And this like also this theorem like comes in a various ideas. Like one of the way, like I think even we have tried to discuss it using like the triangles law, using the yeah, like there are also important applications in various other places, and one of the important application is in quantum mechanics. Again, if you go on further in physics, like you will definitely see this inequality coming over and over again, and it would be very vital for that. And uh, and this is another uh, um, uh, uh, and this is another like important uh, uh, theorem. I mean, not theorem, but it is a technique or a methodology that uh, you see. I mean, you apply uh, for a certain cases, like when you have a set of vectors, but you would see that those vectors won't be orthonormal exactly. They won't be like those you want to construct a orthonormal basis, but you would see that the orthonormality property won't be satisfied. So, but you can extract out the orthonormality for a given number of basis vectors. Like if there are vectors lying around, you can like orthonormalize using this gram set methodology, where you pick vectors like v1 and um, yeah, like let's say if v1, v2, v3 were your uh, vectors, and you see that like they will not be forming a orthonormal basis. Uh, like V1, when you take uh, inner product with V2, like it would be something non-zero. Um, but you want it to be zero because this is what the uh, I mean this is what the usual uh, idea of a orthogonality condition, and also you will see that like norm of v1 won't be equal to 1, and also it won't be for v2. So for such conditions, like what you normally see that like you can like let's say this v uh, let's say you have uh, v1 vector and v2 vector. So again, you can something think of like um, by I mean, you can again use the intuition of a Cartesian space. Like let's say there are two vectors v1, v2 lying in this way on a Euclidean space. Then you will see that v1, v2 like they are not orthogonal. So like, but in order to make them uh, orthogonal, you can use their projections. Basically, like what you can do, like this v2, or basically. Um, this is your if this is your v2, then you can see that you can project out this v1 vector. It's or basically you can resolve this vector. So this is uh, v1 perpendicular, and this is v1 parallel. So yeah, so this is your so then what you can do, like you can um, subtract out the like the you can subtract out the parallel component of the v1 from the v2, and then you will see that you will extract out the orthogonal components of the vectors v1 with respect to v2, and then you will see that like v1 perpendicular and v2, they will be uh, they will form orthogonal at first, and then normalizing them individually will again give you normalized conditions fulfilled. So that will generate you a uh, like a autonomous. So like yeah, so that is what we are doing right here. So here in this case, similarly, you see that v2 perpendicular, we are taking v2 and subtracting out its projection on the v1 vector. So this is the projection on v1 vector, and we are subtracting it from v2, and that will give you only a perpendicular component. And then this v2 perpendicular will be orthogonal to v1, and when you normalize them individually, then you will get this normalized conditions also fulfilled. So that is what, like again, we have seen them uh, uh, during our discussions. So yeah, that was the idea behind. And then and more importantly, as you go, like you have other important uh, topics, and that is your eigenvectors and eigenvalues. So here, basically, we saw like how we can for a given set of equations, or for a given system of equations, like how we can like um, uh, pick out the non-trivial solutions, then uh, eigenvalues used to do that. So, and for a given set of like differential equations for a system of equation, I mean not differential, for a system of like I mean algebraic equations, uh, like if you want to find out the eigenvalues, we used to solve this characteristic equation. And solving this characteristic equation, the roots basically, uh, like this characteristic equation will come in some uh, polynomial expression or some algebraic expression. If you consider lambda as variable, something um, lambda n minus 1 equals to 0. So solving this equation, like for roots of this lambda, like you will get those roots will basically be your uh, non-trivial solutions. So I mean, yeah. So using this lambda values, you will construct corresponding eigenvectors, and that will be basically your non-trivial solution, your final non-trivial solutions for that. And so same way, like yeah. So that was uh, eigenvalues and eigenvectors were, uh, and then the following topic, similarity transformations uh, were useful in the context when you try to uh, see that, like there are certain key things when you study different bases or different like two two different operators, like how they are similar, like how or basically how their bases are similar, or sometimes you want to say that, like one of the directives of the symmetry transformation is diagonalization. Uh, so so for that purpose, symmetry transformations have been introduced, and so like in symmetry transformations, like you see that, like the transformation is basically defined this way. Here, B and A are similar matrices, similar in the sense like they would have same determinant, same trace, and same eigenvalues. So that is what the feature of um, so same eigenvalues, trace, determinants. So one way to see that is like this diagonalization property, where what you do, like like there exists a matrix A. If you want to diagonalize it, then this is the method to do. So you see that yeah, like you go from one non-diagonal basis to diagonal basis. So there you use similarity transformation. That is what the key idea behind, like doing symmetry transformation. You basically go from one basis to the other. So so here you are going from non-diagonal basis to diagonal basis, and this if you have your uh, um, eigenvectors for corresponding to your uh, matrix A. So these are the eigenvectors, and upon diagonalizing it, you'll see that you would end up in this basis. So that is the signature of a diagonal basis. So, and your final diagonal matrix will be nothing but the eigenvalues corresponding to the matrix A. So, so again, this DA is the eigenvalues will be your diagonal elements, because for a diagonal matrix, its eigenvalues are exactly the diagonal elements. So lambda 1, lambda 2 will be the eigenvalues for DA, and also as well for matrix A, because they are similar matrices. They are defined using symmetry transformation. And after all, they are like we are doing a diagonalization here in this case. So then, following it, like then the important ideas about other traits of vector spaces are unitarity and orthogonality. So so unitarity, like again, like you see, it is defined this way. So it is an inner product preserving map, basically. Like it, you'd see like unitary orthogonality has to do with particularly unitarity, like has to do with certain like uh, conservation properties in various contexts. You can see like when you go on to look on its applications, and this unitarity is defined in this way and orthogonality in this way. So if you if you're if you're dealing with complex vector spaces, so this is your condition, and if you're uh, dealing with real numbers or real vector spaces, this will be your condition. So yeah, and then we also saw on hermeticity and symmetry, uh, uh, conditions of your vector space, and that is what has been defined this way. Like again, if you have uh, complex entries, then you will have, if you have dealing with the complex uh, uh, vector spaces, then this will be your condition, and for real, this is your condition. So for real cases, like you call, like if you have a vector, or you let's say if you have operator that is this a, and its elements are all real, then basically you say that this is a symmetric matrix if they satisfy this condition. And if it is complex entries, like if your matrix contains complex entries, then its symmetric property is basically known as hermeticity, or that matrix itself is called Hermitian matrix, and the condition is this, that is A equals to a dagger. So a dagger is basically when you have a vector, you have a operator A, that is your matrix A. You a dagger is basically you take uh, transpose of every elements of its uh, take transpose of every elements of the matrix A, and and consequently take transpose of that resulting uh, A star. So and also one more important thing is like for this harmonicity, like when you are uh, understanding in the context of uh, when you are understanding in the context of uh, um, uh, eigenvalues and eigenvectors, you see that this uh, for this Hermitian or symmetric matrices will always have real eigenvalues. So all these things, like we have seen in our discussion in the vector spaces, like we have covered a lot of examples, like problems we have seen, like, like those problems would be very useful, like if you are I mean trying to take a uh, uh, like a deeper intuition of what vector spaces and how they work. So yeah, that was our discussion on vector spaces, and then we moved on to Fourier series and Fourier transform. So Fourier series again, like taking the spirit of vector spaces, like how we understood like how vector spaces are defined. the same uh, spirit, like we said, like there are certain functions. If we think of in the context of vector spaces, like we can expand them in the basis. With its expansion is basically given like this, where x and its basis and alpha and its coefficients, or technically, or precisely the Fourier series is uh, on such a case that a function f of x is expanded in a orthonormal basis, that is this, where cosines and sines are form a orthonormal basis, like, and also like similar to it, like we've seen an example in vector spaces during our discussion vector spaces, that a polynomial function can also behave like a Rn plus one. N polynomial function can behave like a Rn plus one uh, vector space. They are basically like isomorphic to each other. So yeah. Yeah. So sorry for the interruptions. Uh, so um, uh, I've been facing a lot of technical issues. I know this recording won't be as good, but I hope I will try my best to convey as much as uh, better I can. So if there is any uh, problem that you face during this uh, during when you access this recording session, then please try to reach out to me. I'm just doing a recap of things that we have done so far. So I was talking about uh, uh, ordinary differential equations, and ordinary differential equation. We first talked about linear ordinary differential equations. Then we saw second order linear uh, ordinary differential equations, and in it first we studied the homogeneous case where the RHS is zero, and we've seen some of the uh, uh, cases where this homogeneous uh, ordinary equations were studied. So, uh, so in this homogeneous differential equations for second order, uh, these are certain cases where you can see when you have your roots of the auxiliary equations to be this, you have the corresponding solution. So, similarly, there can be another case where your roots would be complex. In that case, you have your following solution, and or you can also, that is basically you can write M1 is, this M1 and M2 need not to be something uh, uh, equal. They can be even distinct. So in for this case, when they are complex, let's say if M1 is alpha plus I beta and M2 is alpha minus I beta, then you have this solution. So those were the things that we've seen. Other proceeding sessions, we've seen other forms of differential equation, and that is following it we studied the case for non-homogeneous that uh, uh, and second order differential equation. So non-homogeneous, where you have the RHS part to be non-zero this time around. So non-homogeneous case, you seen where your second order equation would appear to be of this form. So you have some function of that is represented as R of x here, and that is your non-homogeneous type differential equation. So this answers that this is your non-homogeneous. And again, your ABC coefficients are constants here. And so in this case, your solution would be a complementary solution, which you basically get from your uh, auxiliary equations, get from auxiliary equations, get for, or you basically get from the homogeneous part, and this is a particular integral. Uh, this is a complementary solution. So this is a total solution of this kind of non-homogeneous type differential equation. And then again, you see like you can go through like we've seen various cases where uh, for different forms of R of x like this, we've seen different uh, like for example, let's say when your R of x was some polynomial type differential equation, or R of x was some exponential type of equation. Uh, so let's say some uh, polynomial type function of nth order of nth degree polynomial, and also it could be some cosines cosine type function, or also sine type functions. So for all these cases, we see is so like what could be your uh, solutions for differential equations, or and also at the end we saw some particular form of R of x. Like some other general form of R of x. So that was given by E of x, H of x. So all these things like we went through and we have discussed how the solutions can be done. So uh, so those were technically the things that like we went through, like the ideas uh, about differential equations, particularly on a uh, I mean, restricting ourselves to a particular structure of differential equation, giving specific solutions to that, and the ways to do that, the ways to determine the solution, like we studied like by mm, judging the appropriate form and structure, we were forming the solution. So that is what the discussion was all about. The linear differential equations, mostly emphasized on second order uh, differential equations. So and moving on, like then we also saw about Fourier transforms. So after Fourier transforms, like Fourier transforms, we already did that. Uh, then there was a new type of transformations that uh, we saw, that is on Laplace transforms. So Laplace transforms was basically defined this way. So the properties that how we defined for Fourier transforms applies here well as well. And so this in, if you have a function of f of t, so in t domain, so if you have your function in t variable domain, upon doing Laplace transform, you go to s variable domain, where you get a function of g of s for the corresponding f of t. And we also studied how this is similar to Fourier transforms and how it is different from that, uh, and various other properties of Laplace transforms. And from there, like we actually also studied Green's functions. So this things like the last bit of topics that we did at the end during our last discussion. So I'm just skipping more of the details, but I'm just reminding you what were the things that we went through. But I would suggest you to go through those. I mean, the presentation materials which is already shared with you. There will be detailed discussion on that. So since we are running short of time, I can uh, just tell you very briefly that what green functions and the one last topic was. So I would suggest you uh, uh, to take a good look on the last few mm, presentation material notes, so that like you can get a fair bit of idea that like what were the things that has been discussed. So in green function, like we basically try to solve inhomogeneous type differential equation, something of this form. Like if, for example, uh, you have some differential equation of this form, then you solve this differential equation using Green's function. So that Green function, say if g was your Green function, then Green's function, then d square dt square g of dt prime plus omega square g of dt prime equal to delta of t minus t prime. So this differential equation basically uh, you used to do a Laplace transform on this. So this Laplace transform basically gives you some Laplace transform of your Green function. So using initial conditions, you can usually, I mean, you can very easily write this. Uh, when first you have to use the initial conditions, and then upon after applying the initial conditions on this, use your initial conditions right here, and after using them you will solve what your Laplace transform of your Green function is. So, your Laplace transform of your Green function would come out to be something, and when you take inverse Laplace, you take inverse Laplace inverse Laplace transform, and that actually give you uh, the form of Green function. And using that Green function, you can construct a solution. So solution was y of t dt prime. So g of t prime, which is your RHS part of your differential equation. So that was the idea behind your Green functions, and then the last topic was on your delta functions. Uh, so I mean that was not in last topic. The delta functions was there before this. So before this topic there was delta functions. So I missed it. I can just tell you like delta functions. Uh, so in delta functions, basically, um, you started with the definition of delta functions 0 for x not equals to a. So this basically tells you that a distribution type function. So, so if this is your x and this is your f of x, so at a point A, you have a spike, you have a some peak, very fine peak. So this peak or this fine peak or this uh, uh, distribution, or like basically this is your delta function, this spike, and that is denoted as delta of x minus a. And so starting from the important property of delta function, we've seen various other uh, um, things, and like we've solved some of integrals using this delta function type uh, functions, like precisely what I mean, like there are test functions and how can we solve them when delta functions appears in the integral. So there are certain techniques and methods that we went through. So again, like I would suggest you to go through them. So, and then finally there was the last topic on series solutions. So in series solutions, basically we saw how differential equations can be solved using this power series method. So method of power series, uh, or like I mean before that, like we understood uh, technically what analytic functions are. So from analytic functions, uh, like we saw what are ordinary points, and also we saw non-ordinary points, or I mean non-ordinary in the sense singular points. So in singular points, we also had regular, irregular, and so for ordinary points, we basically about ordinary points, like we tried to solve differential, was try to solve this ordinary differential equations using the power series method. So and for about singular regular points, like we solved I mean Frobenius method. So in a nutshell, like these were the things we went through, and so yeah, uh, yeah. Again, so in few days, like you'd be having your like first of all, like I want to tell you that like your uh, exams would be like right around corner. So I hope like you can start your preparations as early as you can, and then um, uh, yeah, In addition to that, I wanted to tell you that like, yeah, like you, if you can go through your assignments well, then it would be a, like easy task for you. And yeah, and then and if you understood the concepts as well, that is going to be plus point for you. Like you can tackle whatever the questions you supposed to get in your exams, and yeah, things would be fine. Like it won't be uh, as difficult as it would, because this is a 8 week long running course, and there are many topics in it. And so the important thing is like you understood the basics, and if that is so, then you have already uh, solved your queries or doubts in your assignments. And so the exam would be pretty much straightforward if you have understood that, or if you have covered till that part. And yeah, that will be your uh, course for this register. That would be your course on mathematical methods one, which you have registered in your NPTEL. So you, so that's it. So I mean, that was our uh, last discussion. And so this is a, in conclusion or in nutshell, like these were the things that we focused on more. And yeah, and also yeah, I'm very sorry for the interruptions that I'm having in this recording session. So uh, like I would try, like if possible, there would be, I can try to upload a better recording session upon any request. And uh, so yeah, so and also I wish you all the best to for your test, and have a great time. So this is a very important course. So I hope you like uh, you. I mean, I hope you understand it well, and you uh, keep everything in your mind. Like these topics are really important, really vital for your future, like in various fields, including specifically in physics and also in mathematics. So, so yeah, that's it. And for any other queries, you can reach out uh, for the discussion forum, or there are various other ways where you can reach out for the help. So discussion forums ideally would be the best one. And uh, yeah, yeah, then yeah, that's it. So we so we say goodbye here, and we'll see you again uh, next time if there's a chance that we can uh, get another problem solving session, like discussing this stuff or something else. So that's it. Okay. Bye.